So in this video we're going to discuss and prove properties of matrix transposes. In the previous video we just identified what a matrix transpose is. So in this video we're going to identify that matrix transposes have some properties that we can use when we're working through matrix problems and matrix expressions and equations. So the first property says that if we want to take the transpose of a sum, that we can take the sum of the transposes. That's property one. You'll be asked to prove this property in homework. The second property says that if we want to take the transpose of a scalar C, so remember a scalar is just a real number, so this is the transpose of a real number times a matrix, that we can, this property here identifies that we can take the transpose of the matrix first and then multiply by the scalar. And this will also be proven by you in the homework. This property says that if we want to take the transpose of the product AB, we can instead take B transpose times A transpose. So note here that AB transpose isn't equal to A transpose B transpose. So it has to be B transpose first times A transpose. And we'll prove this property on the next slide. This will be done next slide. And then the final property, which I think is kind of the most obvious of the properties, is that if you take the transpose of a transpose, you get the initial matrix back. And that makes sense. If we take the transpose of A, the rows become the columns become the rows, and when we transpose again, it converts it back into its original form. So for this slide here, what we'll do is give a reasonably formal proof of property 3 so that you have an idea of what to do in the homework. So the proof of 3, we want to prove that AB transpose equals B transpose A transpose. And of course what we need to do is assume that this product exists. So, and that's what's up here. You know, assume the matrix sizes are such that the given operations can be performed. We know we need the same number of columns as we have rows, or we can't take the dot product to do the product. So we're going to make that assumption. So what we'll do is we'll note that we'll look at this guy first. Note that the ijth, so this is the ith row, the jth column, the ijth element of, and we'll talk about the left side first, the ijth element, better make my eye look better, the ijth element of AB transpose. Okay, so what does this guy look like? The ijth element of AB transpose. Well, AB, if we take the product AB and then we transpose it, the ijth element of AB transpose, because we're transposing the product AB, the ijth element, the ith row and jth column of AB transpose will be the jth element of A times B, because the rows become the columns and the columns become the rows. The ijth element, the ith row jth column element of AB transpose is going to be the jith element of the product AB. So we'll say is given by the jith element of AB. So the ith row j element of the transpose is the jth row ith column element of A times B, because the columns become the rows become columns and the columns become rows when we take the transpose, which is equal to, how do you get the jth element of A times B? Well, we know how matrix multiplication's been defined. It's row vectors dotted with the column vectors. Row vectors of A dot product with column vectors of B. So the j'th element of A times B is the j'th row of A dot product with the ith column of B. So that's what the ijth element of AB transpose looks like. The ijth element of AB transpose is the j'th row of A dotted with the ith column of B. And what we need to show is that the ijth element of B transpose A transpose is the same as this. If we can do that, then we've demonstrated that the two things are the same. AB transpose would be equal to B transpose A transpose. So now we need to talk about what the ijth element of B transpose A transpose looks like. So we'll say now, note that the ijth element of B transpose A transpose is given by, what does the ijth element of B transpose A transpose look like? Well, we're multiplying B transpose times A transpose. So the ijth element of B transpose times A transpose is going to be the ith row of B transpose dotted with the j'th column of A transpose. So the ijth element of this is going to be the ith row dotted with the j'th column of the two matrices that we have. So it's given by the ith row of B transpose dotted with the dot product of that with the j'th column of A transpose, which is equal to. So notice the ith row of B transpose has to be the ith column of B, because when we take a transpose, the columns become rows and the rows becomes columns. So the ith row of B transpose is the same as the ith column of B dotted with, and the j'th column of A transpose will be the j'th row of A. So dotted with the j'th row of A. And then what we want to remember is that dot products, the operation of taking a dot product, if we have two vectors R and S and we dot them, take their dot product, that dot products are commutative. So R dot S equals S dot R. So we can take advantage of that to change the order. Ith column of B dotted with the j'th row of A is the same as the j'th row of A dotted with the ith column of B. Now if we look at this statement, we'll see that this statement matches this statement. J'th row of A, dotted with ith column of B, ith column of B, and both of these, this describes right here the ijth element of AB transpose, and this right here describes the ijth element of B transpose A. So if the ijth element of both things are the same, then the two things are themselves the same. So here we can draw a conclusion. We can say because the the arbitrary ijth element of AB transpose equals or is the same as the ijth, I'm going to probably get into my face down here, ijth element of B transpose A transpose, we can draw our conclusion that AB transpose is the same as B transpose A transpose. And that ends the proof of that property. Again, you'll get to do properties 1 and 2 in the homework.